So we left off last time talking about nitrous acid. It's generated in situ by treating NaNO2 sodium nitrite with hydrochloric acid, and what you can do with this is it decomposes to nitrosonium ion, and these are actually considered to be very, very highly carcinogenic compounds. So there is some concern. If you look on the label when you eat any processed meat or hot dogs or things like that, it says NaNO2. Sodium nitrite, that's what they use to preserve the meat. And of course you have hydrochloric acid in your stomach. So this sort of thing can happen in your stomach. And so there's some concern about this. It's been proven to cause things like stomach cancer and bladder cancer in animals, but maybe not in humans. The problem is that it's ubiquitous. They use nitrogen fertilizers, and so even if you eat really healthy and you consume lots of fruits and vegetables, you still will get these nitrosamines in your diet. There's also a little bit in beer, cigarette smoke, things like that. But what they found is that people who eat a lot of fruits and vegetables actually have lower risk of these cancers. So the mechanisms aren't entirely understood, but just to keep you a little aware. So you'll see some meats they claim to be healthier. Instead of using sodium nitrite, they'll use celery extract. Well, celery has a lot of sodium nitrite in it already. And so they're just really doing the same thing. It just sounds healthier, celery extract rather than sodium nitrite. So something to be concerning, but certainly we do need to preserve these meats, because if you don't preserve the meat, you're going to get a lot sicker than right away. You'll get sicker. Later on, you'll get sicker if you get cancer, right? Okay, so we talked about the mechanism. I do not ask this mechanism on the exam whatsoever. And it's really not very synthetically useful for simple amines like this. So we're not going to be doing this. This is not what we're doing. It actually is synthetically useful when you use aromatic amines. Okay, so but let's label this. This is a electrophile with a fantastic leaving group. So can wreak all sorts of havoc in your body when you have a great nucleus. So we call it a really great alkylating agent. All right, so the reaction with primary amines, primary aliphatic amines is not synthetically useful. That's what I just showed you on the previous page. But when you use primary aromatic amines, it's actually very useful. When aniline is allowed to react with nitrous acid, diazotization occurs, the same as we did here on the previous page. And we form an arene diazonium salt. This diazonium salt has a very good leaving group, molecular nitrogen, and undergoes substitution. And so there's a bunch of different substitution reactions we can do with this. Let's first draw the arene diazonium salt. So this is the intermediate. We have a positive charge on the nitrogens that's bonded to the benzene ring. And then depending on what we use, in this case we use hydrochloric acid, we would have Cl- as our counter ion. And this is stable at 0 degrees. So it's stable enough at 0 degrees. When we do it with an aliphatic amine, it is not stable at 0 degrees. So this is stable at 0 degrees, so we can form the diazonium salt in situ. And then we can treat it with a bunch of different nucleophiles. So here's all the reactions we can do with this. So this reaction here, it's called the Sandmeyer reaction. And this is why you want to go back and you want to review aromatic chemistry. You want to go back and review chapter 18. If you had me last quarter, I talked a lot about problems with aniline and our ways to work around that. If you didn't have me last quarter, that is a handout under the practice link. And you definitely want to take a look at that. Okay, so, and even if you had me last quarter, you definitely want to review that. So here's all the things that you can do here. We can replace that diazonium salt with a bromine using copper bromide. We can replace it with a chlorine using copper chloride. We can replace it with an iodine using potassium iodide. HBF4 and heat will replace it with a fluorine. So this is the first time we've been able to put a fluorine on an aromatic ring. Copper cyanide is a way to replace that diazonium salt with a cyano group. So this is our first synthesis of a aromatic, this would be benzonitrile, aromatic nitrile, benzonitrile. Very synthetically useful. If you treat this with water and sulfuric acid and heat, so basically you just would use sulfuric acid as your acid, and then you would just let this warm up. You can now replace that diazonium salt with a hydroxyl group. So this is now our first synthesis of phenols. This is the first time we've been able to synthesize phenols. And then a very kind of different reagent, H3PO2. It's actually called hypophosphorus acid. These numbers are not wrong. It looks a little strange. So hypophosphorus acid. And if you do that, you can replace the diazonium with a hydrogen. Why would you want to do that? Well, there's instances where that's actually a very useful thing to be able to do. All right, so this can be used to remove an amine group. And so let's say we put an amine group on the benzene ring and we use it to direct incoming substituents. Once it directs the incoming substituents, we can take it right back off again when we're done with it. So to remove an amine group, that's used to activate the benzene ring. Or direct an incoming substituent. And sometimes you can actually use it to also to block a position on the benzene ring that you don't want substitution on. Now, as for the mechanism of this reaction, it is not an SN1, it is not an SN2. I'm not going to ask you the mechanism because it's not completely understood. Probably involves radicals, so not SN1 and not SN2. Mechanism not exactly known. And probably involves radicals. Which means there's evidence to suggest that there's radicals as part of this reaction. So one less mechanism you need to know, but also very useful in synthesis and guaranteed you will have some synthesis on the final where you use the Sandmeyer reaction. All right, so let me give you an example of how you would use this in synthesis. Apart from just being able to put these groups on a benzene ring. And we'll do some more in discussion next week. So here's an example. Let's say we want to synthesize the following compound from toluene. So if you think about synthesizing that, bromine's an orthopair director, methyl's an orthopair director. How are we going to get those things meted to each other? Okay, so that's a tricky problem. If you brominate toluene, you will get, and let's say we use two equivalents of bromine. Toluene's an orthopair director, so our major is going to be one bromine in the ortho position, one bromine in the para position. That's our major. And minor, because it's a little bit more sterically hindered, would be to have both bromines in the ortho position. So that's going to be a minor product. And that's only because it's more sterically hindered. But not even close to what we want to make. All right, so let's see how we can do this and get things going exactly like we would want them to go. So instead, what we can do is nitrate the benzene ring and put in and change that to aniline. Okay, so put nitrate, reduce that, and use the amine group as a directing group. So again, all that aromatic chemistry should come flooding back to you, hopefully, at this point. We will get ortho and para. So we would isolate the para, nitrotoluene. We reduce it with H2 palladium. Now, what do we know about this compound? If we brominate that, where are the bromines going to go? So that amine, and so again, you want to look at that problems with amine. That is a very highly activating group. You will get both ortho positions filled. Okay, and you don't want to use FeBr3 because this is so activated that you just throw bromine in and they're going to go right on the ring, even at low temperature. So you're just going to say 2Br2. FeBr3 is not needed. So you see where we're going here. We've introduced an amine, and that amine is doing a great job for us. It's directing where these bromines are going to go. Notice both bromines are meta to the methyl group, which is exactly where we want them to be. And now we can get rid of that amine group. So we're going to do a diazotization. So NaNO2, H2SO4. And you can use hydrochloric acid, you can use H2SO4, your choice. Those are the two common ones, H2SO4 and water. That makes the diazonium salt. That makes the diazonium salt, and then we use, again, you just want to get these numbers right for this one. It's really common for students to change this around. H3PO2. I won't tell you the common mistakes because then you'll do that on the final, but it is H3PO2, so it looks a little strange. And then we get exclusively the product that we want with the bromines, the two bromines, and the methyl meta to each other. All right, so now I've had students say, oh, I have a better approach that doesn't use that. So let me give you an alternate approach to this molecule that also works, that you might have thought of if you hadn't had this problem, if I hadn't shown you this. So let's do a different approach. All right, so we start with toluene, and this is going to bring back some old chemistry from chapter 18. So one of the things that we can do is we can convert that into a carboxylic acid. Remember how to do that? KMNO4, our favorite purple reagent. KMNO4, sodium hydroxide heat, and followed by, and that should be a 2, followed by acid. Why do we have to follow by acid? Because we're making a carboxylic acid in base, so it will be deprotonated. So we need to make sure to throw in acid here. That gives us the carboxylic acid, which is a meta director, and now we can brominate. Two equivalents of bromine, FeBr3. We definitely need the FeBr3 here. And I honestly don't care which method you use here. Whatever works, as long as all the steps work, all the steps work. Now we need to convert that carboxylic acid back into a methyl group. So the way to do that would be to reduce it with lithium aluminum hydride first. And so the reason I'm showing you this is I do try as much as possible to bring up old chemistry so that when you see it on exams, you will be ready for it. You'll remember what that was. So lithium aluminum hydride, this goes back to chapter 20. And then PCC, we convert this to an aldehyde. And now what would we do from 51B? Two possible name reactions here to get rid of that carbonyl. Clemenson or Wolff-Kishner? I kind of favor Clemenson myself. We'll just do Clemenson reduction. Zinc mercury amalgam, HCl. So I'm hoping that many light bulbs are going off in your head to remind you of these reactions. So that's another way to do it. Both of those would get equal credit on the exam. Even though the first mechanism, the first synthesis has a little bit more pizzazz to it, We do like pizzazz, especially when we're grading. You grade 370, exams, and you like when somebody does something interesting. Okay, so it's delightful to see. All right, questions? Anybody? I'm adding 2 new reactions onto this chapter, just for fun. And so one of the reactions I'm adding is nucleophilic aromatic substitution, which is in it's in the newest edition of Smith. I did not have time to cover it last quarter. It is in chapter 18. Okay? If you have the 3rd edition, how many people have the 3rd edition? I will put some practice problems for you. I will cover as much as you need to know about this reaction, and I will put some practice problems for you under the practice link so that you will not have any disadvantage over people who have the 4th edition. Okay? And I do believe the 4th edition is on reserve in the library. Can anybody verify that? Is it on reserve? It usually is. Okay, should be in the library if you want to take a look at it. All right, so we covered in chapter 18, we covered electrophilic aromatic substitution, and that is where the benzene ring acts as a nucleophile and attacks electrophiles, right? So we made all sorts of souped up electrophiles, and the benzene ring attacked. This is the opposite. This is nucleophilic aromatic substitution. And now the benzene is acting as an electrophile, and nucleophiles are attacking it. So if we want benzene, so we're used to seeing electron-rich benzene in chapter 18, and we'd have electron donating groups to make that benzene really electron-rich. If now you want the opposite, and you want benzene to be electron-poor, what would you put on that benzene ring? Electron withdrawing groups, right? The more the merrier, the better, the more electron withdrawing groups. So back in chapter 18, when benzene was acting as the nucleophile, if you put electron withdrawing groups on it, it slowed down the reaction. You got meta-substitution, and you had to heat it up a lot higher. Here, putting lots of electron withdrawing groups actually enhances the reaction and makes it work better. So let me show you what it looks like. So chapter 18, 4th edition, aromatic rings don't react easily with nucleophiles. Nucleophiles can displace aryl halides in highly deactivated benzene derivatives via addition elimination mechanism. All right, so let me show you what I mean by highly deactivated. So, and our criteria is going to be a little more strict than the general criteria. For highly deactivated, we want 2 nitro groups or 2 cyano groups, and I guess we'll do or 2 carbonyls, where of course the carbonyl is bonded directly to the aromatic ring. So we want 2 of them. 2 of these, or you could have a nitro and a cyano group, but 2 deactivating groups. Ortho or para to a halogen, especially fluorine. So I'm going to make these very, very recognizable to you. Okay, you see a benzene ring, you see 2 nitro groups, 2 cyano groups, 2 carbonyl groups, or 2 of any mixture, ortho or para to a fluorine. And that should just jump right out at you because we barely use fluorine at all, right? So those are the best cases, and that's what we're going to be looking for. All right, so that's our criteria. So fluorine's better. This one uses chlorine, though. But notice the chlorine is ortho and para to 2 deactivating group, 2 strongly electron withdrawing groups. And this is what, and so the reason we're introducing this here is this is a way to make aromatic amines, another way to make aromatic amines. So our nucleophile is NaNH2. It is displacing the chloride. What do we know about this reaction? Is it an SN1 or an SN2? What do you think? SN2 we don't want sp2 hybridized, right? So it's not going to be SN2 because we can't do backside attack. Is it going to be SN1? Yeah. If it's SN1, we certainly wouldn't want a bunch of electron withdrawing groups on a benzene ring. If it's SN1, we'd have to make a carbocation on the benzene ring. You know, we would have to make a phenyl carbocation, and having a bunch of electron withdrawing groups on a carbocation is going to not be a good thing. So it's not SN1. It is not SN2. So let's look at the characteristics of the reaction. Strong nucleophile required, so absolutely strong nucleophile required. Water wouldn't work, methanol wouldn't work. Can't proceed by an SN1 because the electron withdrawing group would destabilize this intermediate. So let's draw that. The intermediate that you would use for this, that we're not going to use. Definitely that's looking really bad. We've got 2 really powerful electron withdrawing groups. So no SN1. Let's put a big X through that. Okay. Reaction cannot proceed by an SN2 like vinyl halides. Aryl halides cannot achieve the correct geometry for backside displacement. Aromatic ring blocks approach to the nucleophile to the back of the carbon bearing the leaving group. So let's just draw this out just for a reminder of this because it's been a while since we've had this. So here's benzene on its side. So I'll wedge it to show that it's kind of, so it would be floating above your page. So we know we've got overlap on the top and the bottom. And just for a moment here, let's leave off the nitro groups to make this a little easier to see. Let's put our chlorine here. Can we do backside attack? I mean, basically what this means is this, this electron-rich nucleophile. So we've got this electron-rich, we've got these electrons circulating on the top and the bottom. And this electron ring, what's going to happen when this nucleophile approaches that pi electron cloud? It's going to be repel, right? So is that going to be able to sneak in here into the middle of that donut hole and do backside attack and kick off chloride? Not in a million years is that going to happen. Okay, so impossible to have SN2, impossible to have SN1. Let's do this a different color so you can see what I'm talking about here. It's got to go in here, not going to happen. So none of this either. So SN2 requires backside attack. Which is impossible here. And there is no, and we have already talked about this multiple times, there's no SN2 on sp2 hybridized atoms. All right, so SN1's out, SN2 is out. The other thing that's really kind of wonky here is that the fluoride's a much better leaving group than iodide. So we definitely we're not looking at SN2. So recall in SN2, or SN1 even, iodide's a better leaving group than bromide, which is a better leaving group than chloride, which is a better leaving group than fluoride. And here, fluoride's better. So definitely, we're not talking about the same reaction. And this is worse leaving group. And in fact, we've never seen fluoride as a leaving group in this class. So but we are doing a substitution. So what kind of substitution do we do when we have an sp2 hybridized atom? What do we do instead of SN1, SN2? What do we do all throughout chapter 20 when we wanted to do substitution of an acyl acid chloride, for example? What is that? What is that called? Addition elimination, right? Right? You attack the carbonyl, you kick electrons up onto oxygen, electrons come down, and you do an elimination. So it's the same thing here. It's addition elimination. All right, so let's look at it. Addition elimination. Now, I have so many choices here. I can, what I'm going to do is I'm going to actually tack the carbon that's bonded to the leaving group. I'm not going to do direct displacement, though. I'm going to do addition elimination. So I'm going to have this nitrogen attack here. That carbon, I'm going to move electrons over. And I can go all the way up onto the nitro group. There should be a positive charge on that nitro group, by the way. That's addition. A little bit longer, a little more arrows than attacking carbonyl, but that's essentially what we're doing. And that is the slow rate determining step. Now, there are a bunch of resonance structures we can draw. I'm not going to draw all of them. I'm going to do the two main ones. So I pushed electrons onto one of the nitro groups. I can also push electrons onto the other nitro group. And that's why these two nitro groups need to be ortho or para to the leaving group. Because if they're ortho or para to the leaving group, then we're going to be able to especially stabilize. We've disrupted aromaticity, so we need to do some stabilization of this high energy intermediate here. And that's the nitrogen here. Let's put the nitrogen there. All right, and that was so much fun. I'm going to push on to the other nitro group here, okay? Again, we're leaving out the extra resonance structures. There's a bunch. But what I can do is I can, because of the orientation of these two nitro groups, I can go all the way onto the other nitro group. And in fact, I could have gone onto this nitro group at the start. So you see why we need two of them. So this is a possible mechanism for the final. And of course, we can push this charge onto the ring, 3 places in the ring, in addition to these 2 resonance structures. So my recommendation to you is know how to draw a nitro group. That's the wrong spot there. Let's do this. Know how to draw a nitro group for the final. And know how to draw resonance structures for a nitro group. Okay? So there's our slow rate determining step. It's a high energy intermediate because we've disrupted aromaticity. And now we want to do the fast. Now we want to do the fast step. Fast elimination. All right, so addition, we add electrons, we push electrons up onto the oxygen, and then elimination, electrons come down and kick, and now they're going to kick off the fluoride. Let's see, we'll do it from this one. We could do it from either one. There's a negative charge here. Let's go here. just like that. So electrons on oxygen come back down, and we kick off fluoride as a leaving group. Can you think of a possible reason why fluoride would be a better leaving group than, say, let's do the other extreme, iodide? Why would fluoride be a better leaving group than iodide, for example, here? There's two reasons, so maybe you guys can come up with one of them. Well, let's draw the product first while you mull that over. Yeah, fluoride ion versus iodide would both be. Yeah, actually that would both be kicking off. So that wouldn't be the reason. So substitution. Think about sterics here. Sterics is one of the factors here. Look at where the amine is attacking. Do you see any possible advantage for that leaving group to be as small as possible? Because it's attacking on the same side. All right, so it's attacking on the same side, and it's also more electronegative. So carbon with, remember, we want this ring as electron withdrawing as possible. We want it to be very activated. Fluoride's more electronegative than iodide, so it's going to make that ring even more electrophilic, and that's what we want. So carbon with fluorine attached has larger partial positive charge. Therefore, it is more subject to nucleophilic attack in the rate determining step. And the other thing is, of course, the size of the fluorine. In SN2, we have backside attack, so size doesn't matter here for leaving group ability. In nucleophilic aromatic substitution, NAS, attack is from the same side. So the fact that fluorine is smaller is better. Questions on nucleophilic aromatic substitution, anybody? All right, we've got one more reaction to talk about, and that's the Mannich reaction. All right, so when an aldehyde or a ketone is heated with an acid catalyst in the presence of formaldehyde and an amine, this is the most standard version of the Mannich. There's other versions of this, but this is the one that we're going to be using. The product is a beta aminocarbonyl compound. That should be the symbol beta rather than that. So turn that into a real-looking beta there. So I'm going to go through this, the mechanism, and then we will look at the product. Part 1, and I'm not going to go through all the steps because we've already done this, and you can go back and check how to do this. Part 1, we form aminium ion of formaldehyde. All right, so here's formaldehyde, and we're going to form an aminium ion. So not an imine and not an enamine. So normally when we use a secondary amine, which we're doing here, we form an enamine. Can we form an enamine from formaldehyde? No. You'd need a carbon here, right? We deprotonate that carbon and we form an enamine. So this is what you form. We can't form an imine, we can't form an enamine, so we form an iminium ion. And that's definitely going to be electrophilic. The mechanism for this is page 46 of your notes. Okay, so take a look at that. So this would be a possible mechanism on the final also, because it's got something from midterm 1, it's got something from midterm 2, and then it's got something from this third section of the class. So part 2 is acid catalyzed aldol-like reaction. So the first part 1 is from midterm 1, the second part is from midterm 2 material. And so let's go through that. Acid catalyzed aldol. We've done that before, but let's do it again, because this is a little bit different. So acid catalyzed reaction, we protonate the carbonyl first. We've got hydrochloric acid. I'm just going to use hydrochloric acid to do this. So remember, in the acid catalyzed reaction, an enol is our reactive intermediate. So we're going to make the enol from this. All right, so we've got two bases here. We've got chloride, we have ethanol. You can use either. I'm not going to be particular about this. Ethanol, or you can use Cl minus. I'll just use ethanol here. We're going to remove this acidic proton, push electrons up onto oxygen. So remember, in the acid catalyzed reaction, enol is our reactive intermediate. All right, so now that rather than in the aldol reaction, we would attack another protonated carbonyl, but instead we have this iminium ion that we just made in the first part. So that's what we're going to attack. So electrons on oxygen come down. We attack this carbonyl. We kick electrons up onto nitrogen. So hopefully this is all looking very familiar to you. It's just a little bit of a twist on that reaction. And what you see is going to happen is we've got this amine, and we're going to do an intramolecular deprotonation. And remember, in order to do an intramolecular deprotonation, we need to have a 5 or 6 membered ring in transition state. So if we count, this is 1, 2, 3, 4, 5, 6. So that's exactly what we're looking for. So we're going to deprotonate. Intramolecular deprotonation. So this nitrogen is going to be protonated. And then you can see step 2. In step 2 of our reagents, step 2, we add sodium hydroxide. So then we will just deprotonate this. So here's our final product. So remember, in an aldol reaction, we get a beta hydroxycarbonyl. Here we get a beta aminocarbonyl. So if you see that functionality, you know we can make that using a Mannich reaction. So let's go ahead and draw that up here. Oh, it doesn't like being up there. Questions? Anybody on the Mannich reaction? All right. So, possible mechanism for the final. Mannich reaction is used as a key step in the synthesis of Prozac. We're not going to do the whole synthesis of Prozac, but you can see that this is Prozac, and maybe you might want to, on your own, think of how to finish this synthesis. All right, so we've got our ketone, we've got formaldehyde, we have methylamine here. We have an acid catalyst, and this is ethanol as our solvent. So maybe you want to practice the mechanism on this one. And sodium hydroxide. And then think about how we would take that and do Prozac. So what you can see here is that we have this part done right here. So basically, but this is a ketone, we need that to be reduced. But just think about how you might finish that synthesis to make Prozac. Questions? Anybody? All right, I'm going to save this page, and then we're going to start chapter 27. And we're almost done here. So let me close this. Any questions while we're waiting for that to save? Anybody? All right, carbohydrates. So probably most of you know a little bit about carbohydrates from bio, right? So we're going to just use that as a jumping off point to go a little bit more in depth into carbohydrates. The carbohydrates are the most abundant class of organic compounds in the plant world, so super important. So they're synthesized by nearly all plants and animals. They use them to store energy and deliver to the cells, and then most living organisms take carbohydrates for which they extract glucose, they oxidize it to get CO2 and water and energy, and that's certainly not a topic for this class. That would be a topic for your class, your bio class. Starch, glycogen, and cellulose are all polymers of glucose. Plants store energy by converting glucose to starch. Animals store energy by converting glucose to glycogen. And plants use cellulose as the structural material to support the weight of the plant. All of these are polymers of glucose with subtle stereochemical differences which make profound differences in the physical properties of these compounds. All right, we're going to start by classification of carbohydrates. So there's a little bit of, I guess you could call it nomenclature of carbohydrates that we need to make sure we're all on the same page here. So monosaccharides are carbohydrates that cannot be broken down into simpler units by hydrolysis. You can take a monosaccharide and convert it into smaller units by other means, but not by hydrolysis. So monosaccharides, two examples are glucose and fructose. This is drawn in the open chain form, which you're not used to seeing it in, but certainly there is a small amount of the open chain form when you have a sample of glucose. And so basically we see an aldehyde here. So this is an aldose. So ose means sugar, and ald means it's an aldehyde. You won't be able to tell it's an aldehyde when you look at the closed form, the ring form, which is the most predominant form, but if you have the open chain form, you'll see that it's an aldehyde. D-fructose, on the other hand, is not an aldehyde. It's a ketone. So it is a ketose. All carbohydrates end in -ose, so that means you just have a sugar or a carbohydrate, and ketose means that you have a ketone. So that's classification number 1 that we all need to get down. The other thing is that, and I pretty much use Fisher projections exclusively for carbohydrates. Fisher projections are introduced in chapter, what's the stereochemistry chapter, 5? So Fisher projections are introduced there, but I don't talk about it in my class. I wait till now. So let's talk about Fisher projections. We definitely need to know what to do with Fisher projections. So they look like this, and there's some rules here. Most highly oxidized end carbon on top. So the most highly oxidized is the aldehyde, so that's on the top. Here, most highly oxidized is as close to the top as we can get it, second from the top. It looks like these are Lewis structures, but this is actually conveying stereochemical information. We don't have time to talk about that now. We will continue this on Friday.